Hello everyone. So today's topic is about sequential circuit latch. My name is Shivcharan Puri, Assistant Professor, EC Department, Asansol College. So we know digital circuits are divided into sequential logic circuit and combinational logic circuit. Now combinational logic circuit we have discussed, and sequential logic circuit we have taken the introduction. So what is the difference between them? In combinational logic circuits, output at any instant of time depends only on the inputs present at that instant of time, whereas the logic gate is the most basic building block of combinational logic. Combinational logic circuits do not have memory elements, that is storage device. So these are the characteristics of combinational circuit. It can be designed using gates or available ICs. Examples: adder, subtractor, ALU comparator, parity generator and checker, multiplexer, demultiplexer, encoder and code converters. We have discussed all these combinational logic circuits. In sequential logic circuit, the other category of logic circuits called sequential logic circuits, in which the output is a function of the present inputs as well as that the past inputs and outputs. Sequential circuit include memory element to store the past data. The flip-flop is the basic element of sequential logic circuits. Using flip-flops and combinational logic circuit, any sequential circuit can be designed. Now let's go for comparison between combinational and sequential circuit. Combination circuit and sequential circuit. So for combination circuit, the output variables at any instant of time depends only on the present input variables. For sequential circuits, the output variables at any instant of time depends not only on the present input variables but also on the present state, that is on the past history of the system. Memory unit is not needed in combinational circuits. Memory unit is needed to store the past history of the input variables in sequential circuits. Combinational circuits are faster in speed because the delay between the input and output is due to propagation delay of the gates, whereas in sequential circuits are slower than combinational circuits. Combinational circuits are easy to design. Sequential circuits are comparatively difficult to design. The figure below shows a block diagram of a sequential circuit. The memory elements are connected to the combinational circuit as a feedback path. So as you can see here, this is the combinational circuit, and we attach a feedback path with the help of memory element like this to get the final output. The information stored in the memory element at any given time defines the present state of the sequential circuit. The present state and the external input determine the outputs and the next state of the sequential circuit. Thus, we can specify the sequential circuit by a time sequence of external inputs, internal states, that is the present state and the next state, and outputs. Now, depending on the timing of the signal, sequential circuit can be categorized as synchronous circuit and asynchronous circuits. Let us distinguish between them. In synchronous circuit, the change in input signal can affect memory element upon activation of clock signal. Whereas in asynchronous circuit, change in input signal can affect memory elements at any instant of time. In synchronous circuits, memory elements are clocked flip-flops. In asynchronous circuits, memory elements are either unclocked flip-flops or time delay elements. The maximum operating speed of the clock depends on time delays involved. Whereas in asynchronous circuit, since the clock is not present, asynchronous circuit can operate faster than synchronous circuit. They are easy to design, more difficult to design. So the most basic memory elements we will discuss are latches. Latch is a sequential device that checks all its input continuously and changes its outputs accordingly at any time independent of a clock signal. It refers to non-clock flip-flops because this flip-flop latch on to a 1 or 0 immediately upon receiving the input pulse. They are not dependent on the clock signal for their operation. Okay, so latch is actually unclocked flip-flop, you can say. So as soon as it sees it gets the input, immediately it stores the data. So it is not dependent on the clock. So you don't have any control on the input as such. Whereas the other part is flip-flops. Flip-flop is an electronic circuit or device which used to store our data in binary form. Actually, flip-flop is a 1-bit memory device and it can store either 1 or 0. Flip-flop is a sequential device that changes its output only when a clocking signal is changing. So it will change with the clock. So that is a biggest difference between a latch and a flip-flop. That one is clocked and another is unclocked as such. Now we will talk about the SR latch using NOR gate. As you can see here, this is the SR latch, set to set. Figure shows that the logic diagram of the SR latch composed of 2 cross-coupled NOR gate. Okay, there will be 2 output. Okay, the NOR gates are connected in such a way that the output of one feeds back to the input of another. S and R are 2 inputs of SR latch. Here S stands for set. It means that when S is 1, it stores 1. Similarly, R stands for reset, and if R is equal to 1, that means if this input goes high, flip-flop resets and its output will be 0. This circuit is called as NOR gate latch or SR latch. So let us now go for the truth table of NOR gate SR latch. As you can see here, SR. So 2 inputs are there, S and R. So 2 input means 4 combinations will be there naturally. So therefore, 0 0 0 1 1 0 1 1. So when input is, so when S is 0, R is 0, we will see that the next state, okay, or the output, okay, will be Qn. So Qn plus 1 is equal to Qn. So that means if Q is 0 over here, when S 0, R is 0, okay, it will remain 0. And when S 0, R 0, suppose Q was 1, because this is the output, this is actually the memory, we don't know. So accordingly we have to assume both the conditions. That is, either it can be 0 or it can be 1. So even if there is 1, it will be 1 only. So that means there will be no change if these 2 inputs are 0 and 0. suppose the reset pin goes high, okay, then it will reset 0. So here will be whatever will be Q, there will be 0. The whole circuit will reset. Similarly, when set pin will go high, okay, the circuit will set. So Qn plus 1 is equal to 1. But when there is 1 1 over here, now this 2, because one output is a complementary of another, so there will be error. We will see that actually there will be something, we will get something which will not abide our basic assumption that one output will be complementary of another. We will actually get the same. Now that means it is actually invalid condition or forbidden condition. The truth table for NOR gates SR latch is shown in the table. Qn represents the state of the flip-flop before applying the inputs, that is the present state of the flip-flop. Qn plus 1 represents the state of the flip-flop after the application of the inputs, that is the next state of the flip-flop. Now we will go for the operation using SR latch. SR latch using NOR gates. So now suppose this is a SR latch. There are two inputs, S and R. There are two outputs, Q and Q bar. Now suppose, for assumption, we assume that the present output or the memory is 0. Naturally it will be 1 because of inversion or other complementary output. And suppose this R is 0 and S is 0. Now when R is 0 and S is 0, if we apply this, okay, what will happen? Let us see, but before that, let us go for the final details. So as and this is 0, so this line definitely has to be 0, and as here is 1, this line actually goes high. Okay. So now if we apply R and S as 0 0, what will happen? So 0 and 1, so as you can see over here, the 0 and 1, because it is a NOR gate, so 0 plus 1 is 1 and that inversion is 0, so it will output 0 over here. Okay, so now this changing this line will definitely change this line. If here it is 0, that means that it is, this line is not changed, but because of this feedback path, intensely I am changing it, although it remains the same, like this. So when this is 0, it comes 0 over here. Now what will happen is this 0 0 becomes 1, and this 1 will change here to the same, that is 1, and finally the feedback path will be closed, and 0 plus 1 is 1, inversion is 0. Okay. So what it suggests? It suggests that when R and S or S and R is 0 0, we get the same thing after the excitation. That means Q1 plus 1 is equal to Q1. That means there is no change. Okay. You can also repeat this for 1. Q is equal to 1, Q bar is equal to 0. You will get the same thing. It will be 1 0 only. So that means you will get no change. So for SR 0 0 condition, there will be no change. Now let us go for keeping things same. Let us go for R0 S1, that is set condition. We'll see. So just aligning. So now if it is, if we give the excitation, you can see here, just repeating the steps. Change to 0 now here, and this eventually will make the whole line low, and finally it will affect the whole output path, and you will get here 1, as you can see here. So previously it was 0, now it is 1. So that means Qn plus 1 is equal to 1. You can also repeat for 1 0, you will get 1 only. So that means the circuit is set. Similarly, now going for reset, R pin is high. This R pin, reset pin is high and set pin is low. Okay. So what will happen? If we give excitation, okay. So now what will happen? It becomes 0. So it's unchanged. Now you can see here, it's unchanged. Still high, the line is still high, and now eventually it becomes 0 only. Okay. So that means when R pin is high, reset pin is high, you will actually reset. Okay. You may think that when this is 0, here is 0, or whether here is 0, 1, finally you get 0, 1. You can think like that, but actually you want to just, it is just important to note here that 0 becomes 0 doesn't mean that it is unchanged. If you take here 1 and 0, you will see you will get here 0 and 1. So actually it is resetting from 1 to 0 or 0 to 0, whatever may be the condition. So the circuit as a whole resets or resets to 0. And therefore Qn plus 1 is equal to, so therefore Qn plus 1 is equal to 0. That means the circuit is resetted to 0. But what will happen when R and S both becomes 1? What will happen? Okay, let us see. Let us excite it. We give VR1 1. So as you can see here, it remains unchanged. Similarly, it is unchanged. 0 and 1 becomes 0 over here, right? Now what will happen? This line, now what will happen? Now because of this change, this high line will go low, and because of that, you can see here, finally completing the whole feedback path, you get here the same thing. So if R and S is 0, you get Q is equal to 0 and Q bar is equal to 0. So that's impossible. It goes against our basic assumption because you are not getting here complementary of what is here. So therefore Qn plus 1 is equal to, which is an invalid condition. So forbidden. It's a forbidden state. SR latch using NAND gates. Now you can also construct SR latch using NAND gate like this. So if you construct it using NAND gate, you will get the truth table like this. Okay. So 0 0 now will be now become actually 1, which is actually invalid. 1 means 1 1. So that's the same thing, forbidden state. Okay. Now 0 1 will be 1 set, 1 0 will be reset, and 1 1 will be hold. So from the truth table, it is noticed that the operation of this latch is the reverse of the operation of the NOR gate latch we discussed earlier. The input signal for the NAND requires the complement of those values used for the NOR latch. Because the NAND latch requires a 0 signal to change its state, therefore it is sometimes referred to as SR latch or active low SR latch. Now timing diagram, it will be used extensively. We are just introducing this. So suppose this is the set input which you are applying. Okay, these are all versus t versus time, and this is the reset input which you have applied versus time. Okay, and suppose now you see here what is the output you are getting. Okay, the output, how you are getting this output? You see here at this instant of time. Okay, when as set input is becoming high and reset is 0, so S1 R0, the output goes high. Okay. Now you see here this juncture S0 R0. Okay, what was Q? It was 1. So S0 R0 means no change, it will retain 0 till here. Okay, I'm sorry, it will retain 1 till here. Okay, till here, then it will get this high. What is high? Reset pin is high. So what will happen if reset pin goes high? Q goes low. Okay. Now again, up to this time, this place, it will be low. What after here? You can see here, for this particular region, R is 0 and S is 0, and that means no change. It will keep on becoming low. Okay, till it comes here. As it will come here, it will again set itself. Okay, no change, continue, and finally it will decrease here. It will go to low. Okay, it will go to low because you can see here it becomes high. So you will get the Q timing diagram like this, or the output timing diagram like this. The reverse will follow for the another pin output, because we are following that one output will be the complementary of another output. Thank you.